Hi, this is Snow Day Video 2. For this video, I want to talk about heat transfer. Not just the total amount of heat, but actually moving heat from one place to another and the rate of transfer. We sort of break down the transfer mechanisms into four different um, categories. One is radiative cooling. Things give off heat because of infrared light. The things that are hot radiate in the infrared. Conductive cooling. So heat moves through contact from a warm place to a cool place. Convective cooling, where you are moving a fluid over a hot object and cooling off, kind of like, for example, blowing on hot soup or something like that. And evaporative cooling, removing heat due to evaporating the water. This happens with perspiration. I'm going to primarily focus on conductive cooling. It just is one example of something that we can solve some problems with. So conductive cooling. So our model for this, our sort of physical toy model, is I have a hot place, I have a hot sink, a hot area, and then it's connected to a cool area by some sort of length or distance here, some kind of pipe, a metal pipe or something like that. And the energy transfer depends on the length, on the difference in the temperature, the length that the pipe is, and the area of the pipe. And so it's given this way. The energy transfer is the heat per unit time, and this is referred to, and we use P to talk about power because it's an energy per unit time. And that's equal to the area, so the bigger the area, the bigger the heat transfer, divided by the length. So the longer the length, the lower the heat transfer, times the temperature difference. So a bigger temperature difference will give you a higher heat transfer. And then this K constant depends on the material. So the K constant is the conductivity of the material. So something that's insulating like paper or dowel feathers will have a lower K constant, whereas something like copper, which conducts heat, metal conducts heat, will have a higher K constant. So you use, for example, copper in copper pots to conduct heat from the fire to the food you're cooking, but at the same time you use something with a low K constant to insulate, like down in a coat. Okay, so let's talk about poor Jack again. So what does poor Jack have to do here? So last time we visited Jack, we calculated the total heat he lost, which may not necessarily be a problem if he loses it slow enough. You and I are always radiating out heat anyway to the environment. So if we lose it slow enough, it's not a problem. The problem is the rate at which the heat is lost, and again, that's delta Q over delta T is the heat loss rate. So we can now apply our equation to Jack's situation. We have to make a few assumptions. So again, in this equation, P is the energy flow per unit time, the heat loss per unit time. We're going to take Jack's area to be about 1.2 meters squared. I looked it up. It's a typical area for a person. I would think anywhere between 1 and 2 meters squared would give you a reasonable idea. 2 meters squared would be big. That would be, a LeBron James size person. 1 meter square would probably be a much smaller person, somebody, maybe a gymnast So somewhere in there. So we'll pick 1.2. The length of the heated environment. So this is an assumption I'm making here. That's not very good. I don't know how good this assumption is, and I'm thinking about half a centimeter. Which is 5 millimeters. And what I'm thinking of is the layer of water that's around Jack that he's heating up. So there's a layer of water around him. Let's say it's half a centimeter that he's heating up. And we'll talk about that assumption in a little while. And then the thermal conductivity of water is about 0.6 joules per second per meter, right, per degree Kelvin. So when we plug in all those numbers, I plug in the thermal conductivity of water, Jack's area. Oh, I meant to change this. It should be 0.005, not 0.001. And we're going to take the temperature difference to be about 34 degrees at his skin, which is a little low, but not bad, to 0 degrees in the freezing water. So 34 degrees Kelvin as a temperature difference. And you get that he's losing about 5,000 joules per second, which when you do the conversion is about 1 kilocalorie. All right. So if this was in class, one of the things I would ask you is, what could he change? What are some of the things he could change to affect his heat loss? What could he do to slow it down? And so one of the things, of course, he could do is get out of the water, right? This thermal conductivity, I didn't look it up, but this is much, much bigger than air. It's much, much bigger than a lot of things. Water is pretty thermally conductive. It's pretty good thermal conductor. And so that's the problem for poor Jack here. Another thing he could do is, oh shoot, he could put on a, this is Leo DiCaprio, but my face is in the way. But we'll go with that. So anyway, he could put on a wetsuit. He could put on a neoprene wetsuit. So this is, a foam suit. And it does two things. One, now we're looking at the thermal conductivity of the neoprene wetsuit. That's going to be the important factor. Two, in the searching that I did, what I found with when I was looking for the thermal conductivity of the wetsuit, it gave it to me as a factor of K over L, because of course the distance now, it's not a layer of water, it's the neoprene that you're gotten there. And that distance is more or less fixed. I mean, you can get different distances for different thicknesses for different wetsuits. But this number sort of that I found here takes all of that, the K and the L, and puts them all together. So it's not only the K of the neoprene, but also the thickness of the wetsuit itself, and puts that all together. So in this case, all we need to do is multiply that thermal conductivity by Jack's area and the change in the temperature. And this turns out to be a much, much smaller number than we found, 8 joules as opposed to like 5,000 joules, which is about, instead of the kilocalorie that he was putting out in a second, really this was a small calorie, so 2 small calories per second. So it's 1/500th of the rate at which he was getting rid of heat earlier. So the wetsuit would have been a big deal, right? The wetsuit would have helped a lot. All right, so that's thermal heating by conduction. You'll have a problem on that will go through. You'll have to make use of this equation to do that problem. combined with then the latent heat of fusion. Um, there are a few other cooling mechanisms. There are 3 other cooling mechanisms that I'm going to identify, and you should make note of each of these. These are sort of definitions that I'll expect you to know. So one of the other thing is convective cooling. So the other thing that the wetsuit does is it traps a layer of water next to your skin, and once that layer of water is heated up, you're now not worried about the water flowing past the wetsuit. And you heat up the wetsuit and you heat up the water that's trapped next to your skin, and now the water, you're not going to be dragging that heat away just by having the water flow over you. You get to carry all that with you as you move around and as the water flows past you. So the neoprene wetsuit has 2 benefits. So one of the analogy here is it's a windbreaker for water, right? It also stops the wind. So windbreaker stops the wind from carrying the air that you've got trapped near your body, in your clothes, etc., away from you, and then you have to recool all that air again. Sorry, reheat all that air again. And so now you've got this layer of fluid trapped near your body to prevent the cooling. So convective cooling is another cooling mechanism. Another mechanism we talked about already are changes of state. So also convective cooling also you see happens in boiling pots of water. So in boiling pots of water, you'll actually, before the water really starts to boil, you'll get these convective rolls that carry heat from the bottom of the pot to the top of the pot, and then the cool water moves back down again. Third mechanism for cooling is radiative cooling. Mentioned this. This is anything that is hot gives off heat in the form of infrared radiation, and so we can see that in these infrared photos. In this house, for example, you're seeing where most of the heat is flowing out through the windows, because you've got some infrared cooling that's happening through there. In the cat, you see that the cat's eyes are pretty warm, so the fur is actually keeping it warm, which can sort of counterintuitively means that the outside of the fur is actually cool. Whoops. The outside of the fur is cool, so you're not, in a way, you've got less fur, you've got more of this infrared or radiative cooling going on. So, and similar situations here where you've got some inflammation or some pain, you're going to have more blood flow. That area is going to get heated up a little bit more because of the blood flow, and you're going to get more infrared cooling there. The last cooling mechanism that I wanted to talk about is evaporative cooling. And we're not going to do any calculations with this, but evaporative cooling is when, for example, a person sweats and the sweat evaporates, and because it's evaporating, again, latent heat of vaporization, each of those molecules is taking away some energy, right? So if you evaporate a gram of water, so this could be a problem that we would do. If you evaporate a gram of water, you could then cool by however many, whatever they were thinking, was something like 2,000 joules of heat could be taken away for every gram of water that you evaporate. So actually, this could be a problem that we could actually handle pretty easily, and I may have you do something like that in discussion tomorrow. All right, and that was everything that I wanted to cover. for class today. Obviously, we didn't get a lot of practice in doing things, but take a look at those, and that'll be for the discussion for tomorrow.